This is your workbook, and I've decided now to go through your workbook verbally, and then I will post notes. You should be taking your notes in your own handwriting. This will allow you to go through what I've explained and make sure you understand everything. And when you write things down, you retain so much more. So please take your notes. This time I will be grading the notes. So go with me through your workbook and then take your notes. I'm starting on page 75. So we have talked about the Rutherford and Thomson model, and then it moved over to Bohr. And it started by the discussion, is light a wave or particle? And you will see how this transitioned to electrons and then into our quantum mechanical model that we use today. So the first thing we have to understand is light. Okay, so here's a picture of our light. We have high frequency waves and we have low frequency waves. And what you can see is these, if you think about a wave passing a certain position here, we will have more waves pass through on the high frequency wave versus the low frequency wave. So frequency really means the amount of waves that will pass through a certain spot during a given time. And the other thing I want you to think about is the energy of these waves. Notice in this high frequency wave, we have many more waves in one spot. So think about you standing on the beach of Lake Michigan right here, and these waves are hitting you. Boom, 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 boom. Okay, it's a really wavy day. Down here, low frequency waves, you're standing on the beach here, and they're lapping very gently at your feet. Boom, boom, boom. Okay, so these are hitting you fast and they're coming at you harder than these low frequency waves are. So which one would you think would have more energy? Clearly, the waves beating at you are going to have more energy. So these high frequency waves have much more energy. They're just like the waves that you see in Lake Michigan. Okay, if these were beating against a rock, it would wear down the rock much faster because there's more energy than these waves would if they were water waves. But right now we're talking about light, and they work the same way. And you saw that in that video. You saw constructive interference where the two waves came together and built a stronger wave, a higher amplitude wave. And then you also saw destructive interference where the waves met peak to trough and trough to peak. So they canceled out. And then there were those lull in the water. And that's from that Veritasium video that you saw. I think it's really great. And then he highlighted those waves on the water so you could actually see this interference pattern when two waves came together, where we had areas of higher amplitude and areas where the waves just canceled each other out. And that interference pattern is the beginning of how we came up with our quantum mechanical model, because we noticed some of this was happening with electrons as well. Okay, so let's go to our next page. Light is a form of electromagnetic radiation. Okay, so here is our electromagnetic radiation chart. And notice we have gamma waves. We go all the way down to radio waves. These are the distance, 10 to the 8th. These are the distance of football fields. And then they get so close together, you can't even see how close they are. And gamma rays are, that's, well, it's all radioactivity, but this is the stuff that'll kill you. Okay, why? Well, let's look down at our pattern of waves here. Here's how they look. We get increasing wavelength, but lower frequency. So these aren't as damaging, just like the waves on Lake Michigan. If they're very gentle and lapping, they don't do as much damage. If they start beating against the shore and they're coming really fast, they're going to cause a lot of damage. And these gamma rays are very penetrating through our bodies and they cause cancer. Radio waves, not so much. Common misconception: these guys aren't light. This is all light. All electromagnetic radiation is all light. Okay, so even these gamma rays, which are the radioactivity that'll kill us, that's just a form of light. And so all that we can see as light is this little tiny area that's blown up here. And we have our colors, and you may remember Roy, G, Biv, red, orange, yellow, green, blue, and then they don't have indigo here, and violet. And that's how you could remember the colors of the rainbow. So this is the colors we can actually see, the light we can see, and we don't see microwaves and radio waves, gamma rays in that. Okay, so the speed of light is the speed that all light travels at. They all travel at 3 times 10 to the 8th meters per second. Every single form of light travels that fast. It's all the same speed, provided it's in a vacuum. That means it's not hitting any particles to slow it down. If light does go through a medium, it does change the speed of light. And then when it reflects back into our eyes, which is how we perceive things, the light travels at a different speed. And that's why a ruler in water looks bent to us, because the light coming back at our eyes, it hit that ruler and it slowed down, hitting the ruler and coming back out of the water to come to our eye. So we perceive this bend when really we know that ruler's not bent, but that's why it happens. So wavelength and frequency is related. If I multiply the wavelength and the frequency, I get the speed of light. That means they're inversely proportional. When one goes up, the other has to go down. So it can always equal the speed of light. So if I know the frequency of a wave, I can calculate the wavelength. Now, right here is the symbol for wavelength, and I remember that's a symbol because that little squiggle on the top reminds me of a wave. So lambda here is wavelength, and again, that little wave on top reminds me it's a wavelength. This V is actually nu, and C is your speed of light, that's your constant. So you'll use this to calculate either frequency or wavelength, depending on which one you're given. Okay, again, that common misconception that radio waves are slower than gamma waves. Let's go back up here. This is not true. They all move at the same speed, which is the speed of light, because they're all light. They just have different wavelengths and frequencies. Okay? So, one of the things that led to some of their new knowledge was the photoelectric effect. And this started them thinking again that light might actually behave as a particle, because at this point in time, they decided that light was a wave. And what this is energy of light hitting metal. And some energy popped off an electron and some did not. Now, they hypothesized incorrectly, which is why they needed to come up with a new model. Okay, so the first thing they did was decide that these were energy packets called quanta. So that meant that energy came in these distinct packets, not exactly whole numbers, but they came in steps. So instead of going up a ramp where I'd go through every single centimeter of height, it's like going up a ladder where I go up in chunks. Okay, and they came up with this other formula that the energy equals Planck's constant times the frequency. So if I knew the frequency of a wave, it related directly to energy multiplied by this constant. And Albert Einstein decided that these particles that carried this energy was a photon, and it's basically a particle of light, and that's how Albert Einstein described it. And you could find the energy of that photon using this equation again. Okay, so he decided that matter could only absorb a whole number of photons, and those are those chunks, those quanta of energy. So why did some streams of light knock out electrons and some didn't? They thought that they could raise the intensity and that would raise the energy and knock it off. That means they could raise the amplitude of that waves. That was one of their incorrect hypotheses. I had a hard time wrapping my brain around it. You might too, until I came across this analogy to elephants. Okay, so basically, if I fire a cannon at the elephant, it's going to knock him over. Okay, it doesn't matter if I fire 1 or 100, it's going to knock him over. It has enough energy to knock him over. However, if I fire a ping pong ball, it's not going to knock over an elephant. And they thought that if they raised that intensity, which would be like shooting tons more ping pong balls, and it's low energy still because it's just a ping pong ball, that it would knock over the elephant, but it doesn't. And so that's kind of the analogy. And you can explore that photoelectric effect at this simulation here and the video that really explained this well. And I had another teacher who told me this when I was younger also. Here's a link to that video to explain that photoelectric effect in more detail. So now they're really starting to formulate quantitative analysis where they can calculate things. And they do have some qualitative analysis coming up where they visually see things. The difference is quantitative. Quantity deals with numbers, and qualitative is your five senses. It does not deal with numbers. So they passed light through hydrogen, and they thought they would see all the colors of the rainbow. They thought they'd see the full spectrum. Instead, they saw these distinctive lights. And this was another way that scientists started developing more and more about this theory. Okay, and they're wondering, why do I just have these certain lights and not all the lights through the spectrum? Well, if we're talking about as a particle of light, is these particles, these photons give off energy. If it's in certain packets, you'd get certain lines instead of the whole rainbow as it passes through all the energy levels. So this was just another piece in the puzzle to say that these energies that are given off are in these big chunks, okay? In the Bohr model, really explain this very well. Okay, so I'm going to skip down and go over that Bohr model with you. So what happens is we have this Bohr model where a nucleus is in the middle, and we have these energy levels, which are these rings, and Bohr thought that the electrons actually orbited the atom. That's not true, but this model works so well to explain this that we still use it today. So basically, if I have this electron and this electron is at ground state, which means it's the lowest energy it would be in an atom, it can gain energy and jump up energy levels, okay? And it's absorbing the energy to jump higher. Now, as it relaxes back down, so here is my photon, it's going back down to ground state, back home. It gives off energy to get down. And this energy, these packets of energy, are what you see in the spectrum for hydrogen, and we call the emission spectrum basically a fingerprint for an element. Every element has its own emission spectrum. So as hydrogen electron came down, depending on how it came down, it would emit certain packets of light. And we'll go through that in more detail. When it went up, very interestingly, it would absorb light. And here's the absorption spectrum. And you can see black lines where it absorbed that light, and it's gone because it took that energy away. Okay, so here is a little cutout of our Bohr model. And we have the Balmer series, which I'm going to focus on. You don't need to know the names of the series, but Balmer series is when these electrons went from different energy levels back down to energy level 2. Okay, and this correlates exactly with our visible light spectrum. So when it went from, say, 4 down to 2 or 3 down to 2, it gave off different colors of light. And these lights on our hydrogen emission spectrum are the electron falling from different levels, okay? So we need to understand how to use this Bohr model and how to draw a Bohr model with other elements and other electrons. So here is using the Bohr model, okay? And the Bohr model not only predicts energy of light absorbed or emitted, but we also use it to predict reactivity in elements. It doesn't go over all the properties of the elements. It doesn't explain all of them, but it can predict reactivity. And why is that? Well, here's the picture of our Bohr model. Here is our atom. When two atoms come together, the only thing that touches are these outer rings. And that's because electrons are negative. So when another negative electron from another atom comes near that, they start to repel. So they really can't get much closer than the rings, the two outer rings, having a chance to interact with each other. They don't really overlap and get inside. So these outer ring electrons are called valence electrons, and they are the electrons that participate in chemical reactions. The inner ones do not. They are shielded by these outer electrons. So in order to draw this Bohr model, we draw the nucleus. Here's our nucleus. And we have 11 protons and 12 neutrons. You can figure that out from your periodic table and your atomic number and your atomic mass. Now, for a neutral atom, if I have 11 protons, I have 11 electrons. How are these energy levels filled? Well, here are our rules for filling the energy levels. And basically, our energy levels are labeled with the letter N. So N1 is our first energy level, N2 is our second energy level, N3 is our fourth, and so on. Those are called our primary quantum numbers, okay? And your primary quantum number is your energy levels. And you'll notice on the left side of your periodic table, you have numbers going down. Those also correspond with our periods. Our periods are our energy levels. So this is sodium, and sodium has 11 electrons. My first level can hold 2 electrons, so there's my 2 electrons right here. The second level can hold 8, so I put in 1, 2, 3, 4, 5, 6, 7, 8 more electrons. So right now I have a total of 10 electrons, but I have 11, but this energy level's filled with the 8. N2 can only hold 8, so my 11th has to go in my N3 or my third energy level. And that means my outer shell, my outer energy level, only has 1 electron. So that's your valence electron. So here is an example here. And you can see that my valence electrons, they're only 1 there. Okay. So I'm going to go over this tomorrow, but I do want you to know before we go in there that we're going to be drawing them like this, but our energy levels are not evenly spaced. And here is a Bohr model of a hydrogen where you can see the energy level between N1 and N2 is the biggest gap. That is the biggest gap between energy levels. And then as I go up to N2 and N3 and N4, my energy levels get closer and closer together. So a lot of times when we look at these energy levels, we take a cutout of this Bohr model right here, and we just look at the line. So our nucleus would be down here at the bottom, and then N1 to N2 is our bigger gap. It's a much shorter jump to get to N3, N4 even shorter, and the energy levels keep getting closer and closer together. So now we're going to work on a worksheet and practice drawing these Bohr models. And we're also going to work on introducing the Lewis dot model, which is how we only show the valence electrons in an atom. And that's because when we talk about reactivity, we only care about that outer shell. So Lewis made another model that just shows that valence electrons are the only electrons that participate in the chemical reaction.